Hello viewers, we were talking previously about the occurrence of the lanthanide in the monazite sand. In continuation to it, the extraction of lanthanide from monazite sand, separation of lanthanide by repeated fractional crystallization, solvent extraction method, change in oxidation state by ion exchange chromatography and complex formation shall be discussed. Further, lanthanide third and lanthanide fourth compounds will be discussed. Various hydride, hydroxide and halide compound of lanthanides. Let us see first the extraction of lanthanide from monazite sand. Monazite is major source of thorium and the rare earth. It is a mixture of phosphates as RPO4 type, where R is representing the lanthanide as the lanthanum phosphate. It is honey yellow to golden yellow in color. It is much more heavier than quartz. If you compare the specific gravity, the specific gravity of the monazite is 5.5 and that of quartz is 2.6. So, it is much heavier as compared to that of quartz. It is much less magnetic than other material. In India, monazite occurs in beach sand of Kerala, Tamil Nadu, Andhra, Orissa and West Bengal. The extraction of lanthanide from monazite sand involves the concentration of the minerals. The gravity separation on Wilflet table removes quartz and other gangue material due to the difference in gravity. The gangue is the surrounding of the mineral in which the lanthanide is available. It is dried and separated by magnetic separator due to its less magnetic property. Refined monazite contains the oxide of cerium 30% and other rare earths 32%, thorium oxide 7.5%, phosphorus pentoxide 29% and silica 1.5%. The cracking or processing of mineral by sulfuric acid. Finely powdered mineral is heated with 93% of sulfuric acid at 210 degree centigrade. The phosphates change into corresponding sulphate. After 4 hours, a viscous paste containing lanthanide sulphate and thorium sulphate is leached with water. The lanthanum in +3 state and thorium in +4 state passes into the solution. Silica and zircon being insoluble thus gets eliminated. The acidic solution now treated with sodium pyrophosphate Na2P2O7 to precipitate thorium. The filtrate is treated with oxalic acid, which forms the precipitate of lanthanum oxalate. The mixture is then boiled with ammonium oxalate solution, which leaves behind lanthanum oxalate as a residue. It is then converted into corresponding sulphate by igniting with concentrated sulfuric acid. Now, sodium sulphate is added so that light lanthanides precipitates as a double sulphate and heavy lanthanides as a simple sulphate. The hot sodium hydroxide forms mixture of hydrated oxide of light lanthanide, which is then dried at 100 degree centigrade. It contains lanthanum oxide 17%, ceric oxide 5%, praseodymium oxide 8%, oxide of neodymium 20%, that of samarium 5% and traces of the europium oxide. It is treated with dilute nitric acid to form corresponding nitrates except ceria. The solution of nitrates having lanthanum, promethium, neodymium, samarium, europium separated by the other methods. This is the process how it is getting separated in presence of sulfuric acid. The monazite sand is heated at 210 degree centigrade for several hours in presence of sulfuric acid, which is going to form grey color mud. Then it is treated with cold water. The untreated monazite sand is containing the oxide of silica, titania and zirconia. However, the filtrate is containing the lanthanum, thorium and it is further neutralized and acidified to produce the precipitate of the thorium and the oxalates of the lanthanum and its corresponding hydroxide. The second is the cracking or processing of mineral by sodium hydroxide. In alkaline process, hard sodium hydroxide is taken at 140 degree centigrade. This process allows the valuable phosphate content of the ore to be recovered as crystalline trisodium phosphate. The lanthanide or thorium hydroxide mixture can be treated with HCl to provide a solution of lanthanide chloride and an insoluble sludge of the less basic thorium hydroxide. This is the process for extraction of the lanthanide in presence of the sodium hydroxide, the alkaline process. The monazite sand in presence of 73% of sodium hydroxide is heated at 140 degree centigrade. A mud like composition is viewed in presence of the cold water at 100 degree centigrade. The residue is containing the hydroxide of the lanthanum, mainly thorium, titanium and zirconium. Then in presence of the hydrochloric acid around the pH 3 to 4, the residue is going to provide the titanium, thorium oxide and the zirconium. The separation of individual lanthanide by repeated fractional crystallization, by solvent extraction, change in oxidation state, ion exchange chromatography or by complex formation can be performed. Let us see first the repeated fractional crystallization. It depends on slight difference in solubility of different salts in water. Solubility decreases from lanthanum to lutetium, means if you move from left to right from 58 to 71 towards lutetium, the solubility is going to decrease. Thus, salts of lutetium will crystallize first nitrates, sulfates, bromates, oxalates as well as double salts like nitrates have been used in separation of element because they crystallize as well. In the second method, the solvent extraction, the partition coefficient of salts between water and organic solvent are slightly different. This partition coefficient is also recognized as the distribution coefficient, which represents the distribution of the element in the two immiscible liquids, and the ratio of the distribution is a constant quantity which is known as the distribution constant, and a law is going to govern it, that is Nernst distribution law. For example, the partition coefficient of the nitrate of gadolinium between water and N-butyl alcohol is 1.06 times greater than that of the lanthanum nitrate. Thus, can be separated by solvent extraction with water from a solution of these salts in butyl alcohol. The another method is by the change in oxidation state of lanthanide. Some of the lanthanides shows +2 and +4 oxidation states in addition to +3. The +3 oxidation is the most stable oxidation state as compared to that of +2 and +4 oxidation state. Thus, the occurrence of the lanthanide in +3 is highly stable. Accordingly, they are going to differ in their properties. A change in oxidation state makes remarkable change in properties. Cerium can be separated from mixture of cerium and other trivalent lanthanides by oxidizing it to cerium to +4 oxidation state by reacting with alkaline potassium permanganate. Thus, cerium in +3 oxidized to +4, but other lanthanide still remain in +3 state. The cerium +4 is having a smaller size as compared to that in the +3 state. Thus, cerium +4 state is less basic as compared to the other one and is also having less solubility. Hence, cerium +4 can be precipitated as ceric hydroxide by adding a small amount of alkali, leaving all the other lanthanum in +3 state in the solution. Thus, 99% pure cerium can be obtained from a mixture of 40% of the cerium, means almost 100% purity of cerium can be obtained. Europium can be separated by reducing it. It is the reverse to the previous process. Here it is going to get reduced. The europium can be separated by reducing it to U2 plus state by zinc amalgam. Amalgam means the alloy in presence of mercury with zinc, then precipitated as europium sulphate, which is insoluble in water. The sulfates of all other lanthanides in +3 state are water soluble. So, due to difference in the solubility, it can be easily separated. The ion exchange chromatographic method is much better. It uses cation exchange resin containing sulfonic or carboxylic group with exchangeable hydrogen ions. In exchange process, it is stoichiometric in nature mostly, and the exchange of ions are going to take place at the surface. The aqueous solution containing lanthanides in +3 state is allowed to pass through column packed with cation exchange resin. Then lanthanum +3 ions are replaced by the hydrogen ion. This is the ion exchange property of the resin, means the exchange of lanthanum +3 with hydrogen ions of the sulfonic group or the carboxylic group present in the resin. Thus, lanthanum +3 ion get fixed on resin and hydrogen ion of resin passes into the solution in an equivalent quantity. This is the structure of the cation exchange resin, and it is the sulfonic group containing the hydrogen ion which is getting exchanged. The cation exchange capacity increases with increase in charge on ion, and it decreases with increase in size of hydrated ion. Thus, thorium in +4 oxidation state is having a better capacity as compared to that of aluminum, calcium and sodium. The cation which has maximum exchange capacity is held near the top, and other cation are held further down the column in order of their decreasing cation exchange capacity. So, such type of separation is available in the column. The lanthanum +3 ion are released by using eluent as HCl percolating slowly through the column. The lanthanum +3 ion which is least firmly held comes out first, and very strongly held lanthanum +3 ions comes out at the end of the treatment with the eluent. The lanthanum +3 ions which is least firmly held, these are coming first, and the heavier members comes out first and lighter members comes out at the end. Thus, in a mixture of lanthanum +3, holmium +3, lutetium +3 ions, the lutetium ions emerges first and a lanthanum comes out at the end. The another method is by complex formation. The lanthanide oxalates are insoluble in water, but they can be dissolved by complexing with EDTA. The EDTA complexes differ in their stability towards acid. Their stability increases with increase in atomic number, that is, it will increase from lanthanum, you move towards lutetium. On addition of acid, the least stable complex destroyed first and changes to oxalate, while the most stable destroyed at the end. This is the plot of stability constant log beta of lanthanum in +3 state EDTA complex against the atomic number, and this the value of log beta, the stability constant is going to increase with the atomic number from 58 up to 71 from lanthanum towards the lutetium. Let us see the lanthanum third compound. The trivalent lanthanides are mostly forms ionic salt. It forms more stable complexes with oxygen donor ligand than with nitrogen donor ligands. The larger ions are 9 coordinate in aqueous solution. The aqueous complex of the lanthanide in +3, but the smaller ions are 8 coordinate. The complexation with monodentate ligand is generally weak because it is difficult to displace water molecules from the first coordination sphere. Stronger complexes are formed with chelating ligands. The second and fourth lanthanide compounds, the lanthanum second derivatives of europium achieves a favorable F7 configuration. F7 configuration is the most stable configuration because it is half filled. The divalent halide derivatives are known for all of the lanthanides. Simple salts include ytterbium iodide, europium iodide and samarium iodide. The electride like salts include neodymium iodide, dysprosium iodide and thulium iodide. Many of the iodides form soluble complexes with ether, like thulium iodide is going to form dimethoxyethane. Samarium second iodide is a useful reducing agent. The cerium in ceric ammonium nitrate is a useful oxidizing agent. Otherwise, tetravalent lanthanides are rare. Let us see the hydride compounds of lanthanide. The lanthanide metals react exothermically with hydrogen to form lanthanum hydride, the dihydrides. With the exception of europium and ytterbium, which form black pyrophoric conducting compound. Further, hydrogenation produces a trihydride of type LNH3, which is non-conducting salt. The formation of trihydride is associated with an increase in 8 to 10% volume and greater localization of charge on the hydrogen atom, making more anionic hydride ion in character. The only tetrahalide known are those of cerium, praseodymium and terbium. All lanthanides form trihalide with fluorine, chlorine, bromine and iodine, that is the halogens, having high melting point and are ionic in nature. The fluorides are only slightly soluble in water and are not sensitive to air. It is in contrast to other halide which are air sensitive, readily soluble in water and react at high temperature to form oxohalides. The chlorides are deliquescent, solid soluble in water and alcohol as well. The trihalides are used to prepare pure metal. Some of the dihalides are conducting and the rest are behaving as an insulating material. All of the diiodides have relatively short metal-metal bond and should be considered as two-dimensional metal similar to that of graphite. The graphite is having the layered structure, the two-dimensional structure. The dihalides include those of the europium, dysprosium, thulium and ytterbium. The sesquihalide of Ln2x3 type and Ln7 I12 compounds contain metal cluster. Scandium forms a similar cluster compound with chlorine of Sc7Cl12. Unlike many transition metal clusters, these lanthanide clusters do not have strong metal-metal interactions. Lanthanum iodide is the only known monohalide prepared by reaction of lanthanum iodide and the lanthanum metal. Let us discuss the oxide and hydroxide compound of lanthanide. All lanthanides form sesquioxide of Ln2O3 type. The larger lanthanide adopt a hexagonal structure, while the heavier and smaller adopt a cubic structure. This is the structural difference between the two. All sesquioxides are basic, used to absorb water and carbon dioxide from air, and it going to form the corresponding carbonate, hydroxide and hydroxycarbonates. They used to dissolve in acid to form salts. Cerium forms stoichiometric ceric oxide. It is basic and dissolves with difficulty in acid. Promethium and terbium form non-stoichiometric oxide. So, you can find here as cerium is forming stoichiometric oxide, however, promethium and terbium is forming non-stoichiometric oxides. Extreme reaction conditions can produce near stoichiometric oxide of promethium and terbium. Europium and ytterbium forms monoxide as europium oxide, ytterbium oxide having rock salt type structure. Neodymium and samarium also form monoxide, but these are shiny conducting solid, although its existence is considered dubious. All of the lanthanides form hydroxide of type LnOH thrice. The hydroxide have hexagonal structure and are basic in nature. The basicity of the hydroxide decreases with increasing the atomic number. That is, the basicity will decrease if you move from lanthanum to lutetium. The hydroxide absorb carbon dioxide to give normal carbonates. The hydroxide are decomposed on heating and it is going to form oxides. Next is the carbide compounds of lanthanide. The carbides of varying stoichiometries are known for the lanthanides. The non-stoichiometry is very common. All of the lanthanides form LnC2 and Ln2C3, which both contain C2 unit. Such type of carbides are being formed. All of the lanthanides form a number of borides. The higher borides are insulator or semiconductor, whereas the lower borides are typically conducting. The lower borides have stoichiometries of type LnB2, LnB4, LnB6, LnB12. Next is the carbonate and oxalate compound of lanthanide. The carbonates can be prepared by passing carbon dioxide into aqueous solution of lanthanum hydroxide. It can also be prepared by adding sodium carbonate solution to lanthanum salt of +3 state in solution. The carbonates are insoluble in water, but frequently dissolved in acid with liberation of carbon dioxide. The oxalates of type Ln2O3, the lanthanum are precipitated from Ln+3 solution containing oxalate ion. The precipitate on drying and ignition gives the corresponding oxalate. At the end, the organometallic compounds of lanthanide. The organolanthanide compounds exhibit carbanion like behavior. Because of large size, lanthanides tend to form more stable organometallic derivatives with bulky ligands to give compounds like this and are far less common than corresponding pentamethyl cyclopentadienyl compound of C5 Me5 thrice Cl type. The analogues of uranosine are derived from dithiocyclooctatetrene of Li2C8H8 type. Let us discuss the strategic importance of rare earths in our country. Most of the rare earth producers finding high tech use are related to strategic area, namely in defense area, fiber optic communication, space and nuclear energy. The countries should be self sufficient in using, assimilating and developing the high technology rare earth applications. Dependence on a single country as a supply source for these rare earth materials may not be desirable. Pricing of rare earth products from the viewpoint of developing its market is dependent on its substitutability in various applications and sensitiveness to price of ultimate product and service. Let us summarize. We have discussed the extraction of lanthanide from monazite sand. It was by using the cracking of the mineral by acid, sulfuric acid, and also the cracking of minerals by hot sodium hydroxide, the alkaline process has been discussed. Further, the separation of the lanthanide was discussed by repeated fractional crystallization method. It was further discussed with solvent extraction method. The change of oxidation state, whether it was changed from +3 to +4 or it was getting reduced with the reference of oxidation state. Then the ion exchange chromatographic method was discussed along with the complex formation method. The lanthanum +3 and +4 compounds, their hydroxide, hydride and halides were discussed. The carbide, boride, carbonate, oxalate and organometallic compounds were discussed in detail. In the next episode, we will discuss about the actinide series, the compounds and how they are getting extracted. Thank you.